AI is being used. So there are multiple problems within cybersecurity. So if you look at it, this chart has a lot of use cases being mentioned. So the best use of AI would be in this, in the top two quadrants of, where you have high benefits and high complexity. So if you look at it, malware detection, anti-exploits, um, data protection, these are, very good use cases. These are, really difficult use cases right now within the cybersecurity industry. And then you have things which are, things like UBA, just user machine behavior analysis. I will be trying my best to go into some of the topics in detail. The point is, um, the application of AI within the use cases. So these are some of the use cases where it's really highly beneficial, and it's going to give you the ROI that is really required when you're using a technology like AI. Now, from a security standpoint, from a practice standpoint, we've already started leveraging AI in many of our. So that is something that I can really speak to, where we've already started leveraging it. This was like, I would say, probably a couple of years back, we started leveraging AI in cybersecurity. And right now, as it stands, since we are ourselves an AI company, the use cases are just adding up, to the bottom of the stack. So, and there's no question of, whether this is really required at all anymore. It's become that something that we are already leveraging, and I think it's only going to start expanding to further additional use cases as time passes. So the first commercial application that we really saw in the market, and this is something that we also took in account, is the MDR space, what we call managed detection and response. MDR means, the traditional approach to this was security monitoring, but now um, the approach is actually to leverage um, MSSPs, or managed security providers like apps, to first help in detect, and also to really provide the first level incident response or the containment effort. And so that we are actually seeing the use cases are UBA, which is the user or the machine behavior analysis. So these are high probability incidents which are otherwise really not making much noise, and which are not that easy to kind of respond to, because they're not making a lot of noise within the network. And so there, the usage of AI is definitely helping a lot. The next area is application security testing, and again, this is an area that I will be, delving deep into in the subsequent slides. But that's an again area that has multiple use cases within itself, where we're seeing a lot of traction in customers being benefited by using machine learning. The last use case that I've mentioned here is the malware analysis and threat intelligence use case. So I've actually used the cloud security use case from Microsoft, where they have actually, so they are one of the initial, I would say, early adopters of the machine learning and deep learning actually in the cloud, and they're able to offer this to the customer. So I have added some specific slides on how it's actually helping them shape the future of security, and as to how we, especially with early detection of threats. Now, this is actually a snapshot that was taken from one of our alliance. That the company's name is Dogtrace, and for all the slides, that I've taken reference from certain vendors, I have definitely mentioned provided the reference so that you can go back and look at it. So um, Dogtray is a product vendor that fully utilizes AI, and they're using machine learning capabilities. They have a huge set of algorithms that are actually helping identify significant deviations. So UBA is essentially, so you have, from a security standpoint, we are looking at securing users and machines. And when I mean users, I mean critical users, people like a CEO in a company or somebody who's a chief architect, or a senior developer who's kind of doing coding of a very important algorithm, or maybe the executive assistant of the CEO. Usually exec assistants have more access to information than the principals have. So from a user standpoint, we want to definitely secure the key users of the customer's agency. From a machine standpoint, we're looking at systems which are critical to the business, systems which are, in our language, we call it crown jewels. Essentially, those systems, if you take them down, the enterprise will suffer severely. So the objective of a potential hacker, or for that matter, a group, would be to really take down or go after these crown jewels. It could be either specific targeted users. So they have a whole bunch of mechanisms. So just as I said, there's the reference to the Maitreya framework. We talk about the initial access as to how the initial access is secured. So one of the methods is something called a spear phishing attack, with which essentially they will target a specific user, and then they will send a phishing email to basically take on that specific user. And then once they're successful, that will install, download. Of course, there are subsequent slides on how that is done, but really the key aspect of this discussion is this slide is to understand how UBA is actually helping security MSSPs like apps to identify problems ahead of time. So if you look at this, we have in this specific picture, we have a specific server, and this is a visual representation of what are all the internal targets that the specific server is communicating with. And then the wall that you see here is the perimeter firewall in their agency. And that in turn is talking to a group of assets outside on the internet. If you looked into the live tool itself, and if you click on any one of these threads, you can then actually see what are all the communications happening within within that, and the protocols used. You can also trigger, if it's a live communication, you can also trigger a packet capture, and then actually understand who are all the top talkers for this specific asset that is under purview. Now, the way UBA works is, so there are two types of algorithms. Like I said, there's supervised machine learning algorithms, and then there's the unsupervised machine learning algorithms. Supervised machine learning algorithms depend on what we call specific models that are being developed. And these models will have specific patterns that are, if the system sees a specific pattern is actually present, then it calls it a model breach, which means that specific problem is likely been identified. Depending on the criticality of the assets that we have actually assigned while setting up the system in the first place, it uses that information to tell us if it's a big problem or a small problem, right? So in this screenshot, if you look at it, we have a bunch of systems which are configured, which are part of a specific grouping. We call it clustering algorithms. And what the clustering algorithms will do is basically group these assets into a specific group, and then we are then able to, let's say in this case, I think most of the systems are within certain geography, and so what you can say is all these systems you are used to talking to one of these systems in the other side. But also, if you notice, you have a bunch of other systems here that are talking to a specific, um, destination in the internet, which is a country which is not the usual country that that the others are talking to. This is exactly the type of thing that machine learning is able to help us. I mean, so if you look at this clustering algorithm, these clusters are talking to specific, and they're clustered on the other side. So, but you have a specific bunch of systems that are now talking to a unknown destination. And so if you get into the weeds of what it's communicating, then you can identify whether it's rogue traffic or it's approved traffic, whatnot. But this kind of visibility is something that people in we call them cyber responders. They need this kind of visibility to be able to tell whether the network is really protected, or you can just sit back and think that you are protecting them. The kind of things that we have actually noticed is people bringing in things like as small as a Raspberry Pi and loading it up with offensive security software, just paying somebody in an agency's data center to just plug it to one of the open ports. Now, what will happen is if that system started talking to some, unknown destination and say it starts shipping some exfiltrated data, what will happen is that will show up as another specific asset with the other destination. Obviously, your rest of the systems will not be talking to it. So it's very easy for us to identify. And quickly you can identify things of that sort, which are unapproved, or shadow IT or rogue systems, which are, being introduced into the network. I hope, this gives a sense of what this UBA is. And, from a system standpoint, this is how we solve it. From a user standpoint, let's say you had somebody in the human resources department. This person, let's say every other day log into his computer and access the HRMS, or whatever is the, it could be Dayforce, it could be Zoho Corp, some HR application, in which they're able to do the regular timekeeping activities, or to see who's joining in, all that type of thing. The other systems that they could be connected would be a CRM application that they are using every other day. There could be another insurance management software that they're using as part of their day-to-day job. They could be, keeping abreast of things. So a couple of news sites. Maybe they have some free time, some YouTube, So that could be the regular usage of users in the HR department. Now, all of a sudden, you find somebody logging into Amazon Web Services from the HR department, and they are now logging into some virtual machines, and they're now doing things. So these are things which are, definitely not something somebody in the human resource department would do. So when you do a UBA type of analysis on this data set, what you will find is that maybe that user's machine got compromised, and so the malware or the unidentified potential risky application that is not being introduced into that person's machine is now doing all these crazy things, right? So I hope this gives a bit of insight on the whole UBA use case and the other things that we talked about as to how, I mean, this is an actual application of AI as part of our incident response. Now, to delve into the other topic that we have is the application security topic. Now, in application security, traditionally, if you look at it, we have SAST, which is Static Application Security Testing. That means really examining either manually or the use of automated code to identify potential software flaws in the source code of a software. That's it's called SAST or Static Application Security Testing. Now, then of course, we also have DAST, which is Dynamic Application Security Testing, which means really, pen testing in applications like how hackers would, and then trying to find out problems or security issues and flaws in the application. Now, the industry has moved on from both these approaches, so they still exist, but now the new way of solving the application security challenge is the interactive application security testing, or IAST. So we also have an alliance, and the partner in question now is HDev. So I've given the link to their website as well. So IAST is a way. So for those on the call who are familiar with web application firewalls, or WAFs as they're known, it acts like, if you look at the way it's been implemented, it's something like a WAF, but really it sits in the between the users and the actual web servers. So it sits in the middle, and then it's able to use that, it leverage its position to not just look at traditional OWASP-based attacks, but also any potential flaws in the business logic in the applications. So for those of you who are new to security, or you're just trying to delve into application security per se, is that I think somebody needs to go on mute. So OWASP is the standard. Again, there are multiple other standard like SANS, but OWASP is the most utilized standard that defines what are the top 10 type of vulnerabilities which are affecting web applications per se. So a traditional WAF, or web application firewall, would basically sit in front of the web servers, and it's like a shield. It just sits in front of the web server. It takes all the attacks and would protect the underlying web server against the web application attacks. Now, what they have done in the case of IAST, what they have done is they have added that WAF capability plus machine learning capability to understand what are all the usual type of requests that comes to the to the web server in the given web server in the normal state. So that is actually being recorded by the machine learning and learned. Now, again, so the algorithms used are unsupervised machine learning algorithms. Now, the moment that is done, when you're seeing an attacker, so attackers will not just use the same logic. They will obviously try to do things which are not the normal. So they could try anything between trying different types of methods to talk to the web server, or they could try different parameters being injected for what we call as injection flaws. So if you look at the initial e-commerce days, people could just change the values of the products in the cart. Like if something cost 50 rupees, people would just edit the field and submit as 5. And if there was no validation on the server side, the whole order will get completed with just 5 rupees on the cart. That has actually, it has happened, and it was published, and of course the whole server side validation came in place. So even that type of things will be actually stopped by things like IAST. So this is again another classic use case of how machine learning is actually able to help secure the applications. The other area in application security where again AI is predominantly taking space is the testing. So for those who are familiar with software development, um, a critical part of the whole non-functional requirements is security. And as you know, as folks do functional testing, they will also do non-functional NFR testing. And one of the components that's being done is security testing of the application, and that's exactly where the SAST and ST came to play. Now, in today's environment, most of the tests are, I mean, at least some of the tests are still completely manual. And some of the tests are being automated by things like Selenium. But what still remains completely manual is the identification of use cases or the test cases. Um, so now this again, this product is again another alliance that we have, and their unique approach to this is that now testing. So the way it works is they have a platform, and then you can submit your software code, or you know you can submit your repository for the, of course for the product to scan. And it's able to scan your code and then identify different use cases, and that could include security test cases as well. So after that, you can either again execute the test manually, or you can leverage its own capability to make some automated tests. So this is again a significant space where we're seeing AI to be again, but it's a I will not say this is a very mature state like the other UBA use case that I was talking about, but it's starting to take shape, and we could see potentially a lot of testing being automated through platforms like this. In the interest of time, we will delve into the next topic in question, which is the how AI is actually being leveraged by cloud security models and cloud security players. I mean, cloud players like Microsoft. Now, if you look at it, there are the way somebody in the cloud would manage things is they have two different types of ML engines being used. So there's the there's of course there's the cloud component, and then there's the client component. When I mean the cloud component, things that actually run in their side, I mean in their infrastructure. And then the client side is basically they will have some endpoint security software or something that can actually sit on the end computing environment. Like it could be a laptop, it could be a server, it could be but they will have a small agent that's able to sit inside these components and then collect information, um, and that information is actually used to model some of the algorithms. Now there is a pre-exec and post-exec engines and models, and we need to understand what those are to really understand how it's being leveraged. So we will first go through the first, the top left quadrant um, to understand, or we will actually, we will start with the top left quadrant in the bottom to start with, because that is exactly where things start. Now, in the in any client software, it will have certainly a certain percentage of known techniques and attacks, as to how things are being introduced. So like I said, the initial access of how things are being introduced into your environment. So let's take some use cases, to really help us understand how this is being happening in practice. Now, let's say there's a user who's just browsing, and then this user comes across a specific website that says, hey, I will let you access this service provided you download and install the software, or it could be, I will let you access certain pieces of this website provided you install this add-on in your browser. So that initial access, the way they to try to establish that initial access, or they could have, they might as well send you a small attachment as a PDF or a Word file, and that could potentially contain malicious, or could have other scripts that can, kind of pull malicious um, material, code into your system. So those are the type of things that, form the patterns to understand how that initial pre-execution, um, the application logic would look like. So once that it has a good handle, most likely the client side ML will try to look at those patterns, and most likely, it'll actually help you. It'll block the threat, or it'll stop you from doing something which is obviously, going to damage your system. On the cloud side of this, what is there is that you typically look at a collection of all these different events, being pumped together, and it's typically all these digits are sent as JSON files. It goes there, and that is forming the whole metadata content as as a huge crowdsourcing database that's now available with the provider like Microsoft. So typical things which are done is they run a IOC extraction process of the different files that are being used, different file hashes of the processes, important key detection, metadata that's been obtained, like be it kernel calls, what type of interactions with the hardware that was done, any specific bugs that were raised, EMET events, all of that basically gets pumped in, and that is used by some of the different models which are present there. Some of the models are specifically geared towards identifying reputation, and what we mean by reputation is if a certain IP address has or a certain product vendor is known in the past to producing things which are malicious, or definitely not in the right intent, they will obviously have a negative reputation. And when this whole reputation engine ML is basically triggered towards identifying who has the good and the wrong reputation. And once they're able to funnel it up to a point where they know where the unknowns are, and those unknowns are actually then used for further analysis. And so then they look at the detonation based ML. So basically, these are potential sandboxes that are available within a cloud provider's environment, and then they will use that information to see if they are able to detonate few files, new files that they are able to find, new IOC. It could be PowerShell scripts, it could be new applications. They will basically detonate them in some of the sandboxes, and then identify what the behaviors look like. That is again pumped into those algorithms. And definitely file classification MLs are those which are essentially looking at the data classification and the data governance standpoint. What are the types of files that are really being moved around in the environment? Are they classified files? What I mean by classification is, so right now there are every environment, every protected agency will basically have either automated or manual means of classifying. So this presentation, for example, that I'm sharing with you, has a classification called public in the bottom, if you notice. So which means it is really, there's nothing confidential here, and it's okay to basically share it outside our agency. So if it has any other classification, like either be it proprietary or like say GAPS internal, or it has a confidential classification. Obviously, I shouldn't be screen sharing to this to you guys right now. So that's the type of metadata that it will look for to identify and see if some data exfiltration has actually happened with the given IOCs which are being pulled up from the client environments. Yeah, this is on the pre-exec side of the house, and then let's say no matter what was done, the user either bypassed the restrictions, or the threats were so good or new that it actually ended up um, being executed. Then in that case, um, essentially, look on the client side of the house, we have something called AMSI, which is just a technology that Microsoft introduced from Windows 10. It's called anti-malware scan engine interface. Potentially, most of the antivirus solutions, even today, are blind against fileless and in-memory threats. What I mean is, for them to be able to successfully identify, contain a specific threat, it has to be present on the disk. And the new threats today are leveraging things like PowerShell, VB script, to have you all the latest mechanisms to download. And I actually, as part of the subsequent slides, I actually have information on how this is actually being done by the latest threats. But just to simplify the idea, there is Microsoft really gave this new feature called AMSI integration, where that can actually help antivirus software to interface with this whole new engine that Microsoft has provided, and use that to identify in-memory and completely fileless malware. So the network is also monitored to see the type of connection. So usual ports protocols that are being used to connect to the outside world, that is being monitored. There's again the whole memory scanning, in-memory scanning, that identifies what type of processes are running. The usual there's a there's a hash verification of the processes that happens. Also, the pattern in which these processes are being invoked are being scanned. Like I said, there's the behavior monitoring in place, like typical API calls, typical the file IO activities. Are they looking, if it's a ransomware, obviously that it has to touch a wide range of files. Now, with that type of huge IOPS activities, certainly something that gets into the scanner is is these algorithms will start kicking in, see, to identify and see. So typically they will put the process on hold, ship all these IOCs to the cloud-based engines, and then wait for further instructions. So there is actually a whole workflow on how this is actually happening on the subsequent slides. But this information is basically, it goes up the food chain to the provider level, where there are specific AMSI paired MLs which are looking at just those patterns alone, and then there's behavior-based ML patterns which are looking at just the behavior, be it the file interaction, network interaction, and the kernel calls. So, like I said, there's a bunch of scripting that happens, and then emulation that happens where this was actually emulated in one of the sandboxes. There's execution, and then of course there's post-breach behavior. Post-breach behavior could be once the attack is successful, any outcomes out of it. Typically, if you look at it in the real world, it could be anything between bad exfiltration, or it could be it could be running a crypto miner in the target environment. It could be deletion of files if it's a ransomware, encryption of files if it's a it's a ransomware case, or it could be taking down systems. Those are post-breach behavior. So like I said, there's this is the whole these are different stages in which these engines are configured to get the information based on the different models that are present in the environment. So this is the logic that I was talking to you about. So there's the client side script engine. So they're typically looking at the content hashes and the client side behavior models. And those are being shipped. So the up to the cloud engines. essentially what they're doing is they're crowdsourcing the different IOCs present in the client-side environments. They're crowdsourcing that to specific model engines which are present in the cloud. And this is actually helping them, and like I said, they have actually gone to a point where they're doing some really interesting research with this type of thing. Actually, they were able to prevent several types of attacks since 2018, depending on this model, and they're potentially able to stop a lot of threats before they could just become rampant and attack a lot of enterprises. So there's a ranking logic. So again, this is ranked by machine learning. Like I said, based on the type of attack and based on, of course, this is exactly where this is the place where reinforced learning is actually used, and they will have security analysts in the back end who are providing inputs to these algorithms and telling that, hey, this is a good find, this is of course not a valid find, things of that sort. So the more you start pumping in that type of information to a system, it actually helps the system learn over course of time. And that's exactly where reinforced learnings are used. And then finally, like I said, if it finds something suspicious, it will actually put the process on hold. And then once it gets the decision from this engine, then it will basically either block or abort the script, or it'll actually allow you to run the specific app. And this is the whole instrumentation logic behind how some of these technologies are used right now. So this specific slide that I actually had in place is to really show you what are the different stages in which it's taken through. So there's you have a typical process. So this could be the initial stage. This could be anything like could be either a Microsoft Word file, and it could be PDF. They typically target Office or Adobe vulnerabilities, uh, and use it along with it. Could be the other one could be either a spear phishing attack, or it could be somebody putting in a USB drive. And when it gets executed, obviously it's going to leverage um, the vulnerability itself, to exploit the system. And then it takes, typical PowerShell, or in this case, which is showing an example of how it's taking PowerShell, and how it and some of the common methods which are used to inject and the process into the memory. And once the process actually into memory, that is the stage where they will do some process hollowing. Now, process hollowing is a mechanism where so traditionally, the moment you inject anything into the memory, all of a sudden, the AV engines, the antivirus engines that are there in the environment, they will quickly get alerted because obviously there's a kernel call for a new process. And so immediately they will try to scan the whole the process. They'll basically dump it into from the memory, and then they will basically look at it for possible malicious behavior. Now, the attackers on the other side, they figured out this is how they're doing it. So what they did was, initially when it's coming into the memory, it'll come clean as so if you really did a scan, it'll not have anything seriously problematic into it. So it'll look like a very genuine application. But once it gets loaded into the system and it thinks that it is, pretty sure that it has passed the AV validation stage, so those are, we call them defensive techniques and evasion techniques. Then what they do is they will then make a call to download some of the additional executables from their whole own CNC network, and at that stage, they will basically add all the malicious code into and then that's the stage we call it process hollowing. So once that is also over, then it again tries to change its name if required, just to again be different, more evasive. At that point, it is really ready to start, doing that. And so in that stage, that is a stage, where these techniques of how the injection is done. So these process tree behavior models actually help identify that type of activities, and then that is actually being again crowdsourced into the machine learning models in the cloud. And just like I explained in the previous instance, there's a reinforced learning algorithm that decides and ranks the issues, and finally that's being used to decide, and the action is taken whether to allow or block the traffic. I mean the application, which is or the traffic in question. So again, this is another slide that actually shows how this whole process. So you have Outlook.exe, which is a a mailing application, and somebody gets a Word file here. Word file has a macro, and prudence tells us that we should not enable macros from unknown sources, but who listens, right? So they anyway, they enable it, and then so that they make a call to WMI, which is the which is the channel that they use to launch a PowerShell. So PowerShell gets launched, and once PowerShell gets launched, there's a new process that gets injected. And if you look at this, this is the 986.exe is the, it looks this, this is the genuine code. So it could be as genuine as something like a calculated application. So your typical AV engine will kick in at this point and scan this application, and then it might even tell you that it's not malicious, and that's exactly when they wait until that time. They will not make hasty decisions. They will basically take the time to use their defense evasion techniques. So this is when process hollowing will kick in. So that point, they have the additional the executable code being injected into it, and now you have a whole new target. I mean, new application that comes out of it. At this point, it is actually ready for being weaponized because it has all the, so typical actions that would be, injected at this point is things like mimikatz. I don't know how many of you have heard of mimikatz. Mimikatz is a credential stealing, um, you know, um, uh, hacker application, I would call it, and that's predominantly been weaponized and used a lot of ransomware and other thing. Or it could be any ransomware type of thing that gets padded, or it could be some crypto mining. So all that is kind of added at this stage where it says cycle targets here. That's the stage when it all of this is added, and then now you have you have these different vectors that you're looking at in the bottom of the screen that is actually helping them weaponize the whole process. So at this point, I think I've spoken enough, and I would want to open the floor to possible questions that I can answer from now.
Participants, if any questions, you can either post in the chat box or unmute yourself and ask. Sir, one question, sir.
Uh-huh.
What are the major drivers and opportunities of artificial intelligence in the security market, sir?
Uh, I'm trying to get the question right. Major drivers and
Opportunities of artificial
opportunities.
intelligence in security market, sir.
So the key driver is obviously in our industry, and the major problem we have is something we call as alert fatigue. Alert fatigue means you're tired of seeing the alerts, right? We have security analysts who are again it's a follow the sun model, and they're looking through the alerts and logs 24/7. At a point when you get so much of alerts, there's definitely the problem that people are tired of looking at it, and sometimes that may even result in somebody overlooking it, somebody not looking at something very critical. So the chance and possibility is somebody will just overlook is very high, and it's I mean, not that they're not bothered, interested. I mean, even if you look at the army personnel who are posted in the north, at some point, they may be really tired because they're fighting a war, right? So this is no different from from them. I mean, they are fighting it in the physical world, and we are cyber responders are fighting it in the cyber world. So really helping them, and if you look at it, when Target, I don't know how many of you know Target here. Target is one of the largest corporations in the US, just like Walmart, and they got hacked way back. They were using a product called FireEye, which is one of the most leading products then and now when it comes to defense. When they were being attacked, the attackers did multiple things. So they had the responders were actually having about tens of thousands of alerts that they had to basically look at. Think about it. I mean, you have a problem now, and you have 10,000 to 20,000 alerts that you have to look into to identify, where the problem, and that's a starting point for them. It was really difficult. So when you have things like AI, it can really help you suppress the noise about the things that really matter. So that can really, help them. So essentially, if they had AI back then, they would only be looking at one or two specific targets that just got compromised. So at least where your starting point is. You don't have to dig in for 5 to 6 hours, especially when when everybody's behind you. You don't have that kind of time, and that's where exactly AI can help. So that is the biggest benefit and opportunity, is this. And then from like I said, one of the previous slides, I did talk about detection, prediction, and response. The every other agency in the world wants to reduce the time taken for response. They don't. For example, if I have to really depend on humans to block a certain IP address or disable a certain user account because it's been affected, they will take their own sweet time. It could be 2 hours, 3 hours, and that time will actually cause the damage to further expand. So if it was done, if it was AI, it would just take probably a few seconds to identify it and then block it. So the opportunity is really reduction of reduction of noise. The opportunity is a reduction of time taken to or the dwell time to identify incidents, and of course the time taken to give the first level incident response. So all that are really good opportunities. Any other questions?
Thank you, sir. Thank you for answering the question, sir. Any other questions from the participants? Uh, Thank you, sir. Uh, Thank you so much for your valuable session, sir. Thank you for sharing your knowledge and valuable inputs. I hope all the participants would have gained valuable insights on the topic of this session. Thank you.